In this next video, we're going to go ahead and cover this exact example using the limit definition of the integral. So again, the idea is we're trying to evaluate the area under the curve, this thing right here. What is the area of this exactly? Not approximately, not using a finite number of rectangles, but an infinite number of rectangles. Well, keep in mind that for me to do this, I need to use this formula listed right here. So I'm going to go through detail by detail. First thing I'm going to go ahead and find is delta x. The reason why I'm going to find delta x is because it's in this formula, and you'll notice back up here that delta x is in the formula of xi. So delta x is b minus a divided by n, where b is 4, a is 0, and it's divided by n, which again, we didn't specify any number of rectangles, so n is going to remain as n throughout this entire problem. So I'm going to have 4 divided by n as my delta x. Next, I want to find x sub I. Again, it's a very special x value selected in those infinitesimally small rectangles that's going to guesstimate or approximate the height of that rectangle. So xi in this case is again a plus I delta x. Well, I is going to be a variable, n is going to be a part of this delta x, which is going to be a variable, and a should always be a number. So my a value happens to be 0 in this case, because that's where I'm starting. That's my a value. Plus, my delta x is 4 over n, that we found right here, and I remains where it is. So my my xi is 4i divided by n. So now I have delta x and I have xi. Now keep in mind in this formula I have delta x, I have xi, but I need f of xi. So in my next step, I'm going to go ahead and evaluate what f of xi is. Well, keep in mind, f of x is the function inside the integral. So that means I'm looking for if f of x equals x squared, I want f of xi, which means I want this thing squared. Again, xi is 4i over n. Now one thing that might be unique or interesting to notice is that notice there is no x value in xi. Delta x absorbs the x value and creates it into an n value. So in this summation, there shouldn't be any x's left over once I've plugged in f of xi and once I've plugged in delta x, which means that I'm going from I equals 1 to n, and this thing should simplify down appropriately and efficiently to something without x. So my next step is I'm going to go ahead and type in all of the pieces. Now if you'd like, you may first start off with just go ahead and look at I equals 1 to n of the summation of f of xi times delta x. By leaving out that limit, you're allowed to do this. However, that limit must be back in there at the end. So this summation is equal to the summation of I equals 1 to n of, I'm going to go ahead and simplify this right here, 16i squared divided by n squared. And that thing is multiplied by my delta x. Don't forget to plug that delta x into that summation. So right here is our summation value, and I'm going to go ahead and simplify that a little bit further. Remember that I can go ahead and multiply everything in here together, and all constants can be factored out of this summation. By constants, remember we're referring to anything that is not specifically added or subtracted to I. So when I multiply 16 times 4, and I end up with 64, and I have n times n squared and get n cubed, I can factor out 64 over n cubed outside of that summation, where I'm left with I squared. Now this summation should look familiar. The summation we've worked before. The summation is one of the values we've worked with in terms of those formulas. So recall the summation of I equals n times n plus 1 divided by 2, and I squared happens to be n times n plus 1 times 2n plus 1, all divided by 6. Okay, again, I remember that there's a clear pattern between these two pieces, such that n and n plus 1 are still in there, such that the 2 is still in there, and now I have a 2n plus 1, and a 3 added to the bottom in a multiplicative form. So this thing becomes 64 over n cubed times, when I evaluate this summation, it is this thing right here, down here, assuming it starts at 1. So I end up with n plus 1, 2n plus 1, all divided by 6. So my last step to this is to simplify this, and remember, this is not done if I'm just evaluating the summation. The formula for the limit definition of an integral is to take the limit of that summation. So what I'm going to do down here now is say that the integral from 0 to 4 of x squared dx is equal to the limit as n goes to infinity of this entire thing. Again, notice we've evaluated the summation. The step that we first do is find out all these formula values, delta x, xi, f of xi, plug it into the summation, evaluate the summation, plug that into the limit, and evaluate the limit. Now I'm going to cancel some things out as I go. This n cubed can cancel out with n and leave me with n squared on the bottom. The 64 and the 6 can cancel out, leaving me with a 32 and a 3 on the bottom. So now I'm going to end up with 32 times n plus 1 times 2n plus 1 divided by n squared times 3. Okay, this is almost done. Our last step that we have to do is simply multiply everything out and evaluate this infinite limit. We have to remember, however, how to evaluate an infinite limit. So before I actually do that, I'm going to go ahead and FOIL this information out, see if I can cancel as much information out as possible. I am going to factor out 32 over 3 outside of the limit because it is a constant multiplied by the entire limit. It is a constant 32 over 3 multiplied by everything inside here. I can factor that out. So down here, I'm going to end up with n times 2n, n plus 1 times 2n plus 1 is actually going to be 2n squared plus looks like 3n plus 1, all divided by n squared. So I'm going to distribute this division of n squared to each piece, and note that this is 32 over 3 times the limit as n goes to infinity of 2 plus 3 over n plus 1 over n squared. And the last thing that we need to remember is that in infinite limit, we only have one real rule. That rule I'm going to write over here is the limit as n goes to infinity of something that's a constant divided by n is always going to go equaling to 0. So that means that this equals to 0, this equals to 0, and this equals to 2, which means that this limit overall goes to simply 2. So I end up with 64 divided by 3 as the area under the curve of this function exactly, not approximated, exactly, given that we've taken this region and sliced it up into an infinite number of rectangles and evaluated those areas added up.